The question is, what is time? And I guess you all know what is time, right? Time is the thing that distinguishes now from this morning. There's a now, then wait a moment, there's another now, there's this long sequence of instants. So we can figure out this long sequence, this long line, which is time. So I've decided to make a picture of time as a long line. It's very long, so I go there. So that's a metaphor of how to think about time, which I'll use. We're here. This is a minute ago, this morning, yesterday, the year before, and so on and so forth, right? This is the future, which is not yet to come. Let's mark the here. We're here. So actually, we're not here anymore. It's moved a little bit in the middle. Right? So it keeps moving. And of course, the future is very different from the past. The past is something we have pictures about, we have memories, we know what happened has happened. The future, we don't have pictures about it, we don't have memories, we don't know what happened. We know a little bit, we can compute some things, but most of it is completely open. The interval from one point of this line to another point of this line, we can measure it with clocks, the amount of time that passes. And clocks are devices which are meant to measure all the same interval. So the interval between here and here, say my talking will be over in 40 minutes or something like that. So it will be 40 minutes for all of us, right? All the clocks will go ahead 40 minutes. That's a picture of time we have. It's a common sequence of instants. We're all together, moved a little bit. We're all together in the universe, all together. The entire universe is in this moment of time, and then the entire universe is the next moment of time. And in some sense, it flows, it passes. Right? We're passing from one. Things move into the past, we have memories of it, and we go open to the future. This is time. Almost everything I have said is wrong. It's factually wrong, okay? It's wrong in the sense in which we say that to say that the Earth is flat is wrong. Or to say that the Earth is still, does move, it's wrong. Okay? We know the Earth is not flat, it's round. We know that the Earth does not, it's not still, it moves, it spins. Nevertheless, we can usually think here that the Earth is more or less flat. If we build a house, we don't have to care about the curvature of the Earth, and we don't have to care about the fact that the Earth is spinning. We can easily think the sun is going up, the sun is going down. We know it's not true. The sun is staying there. We are moving. Right? In the same sense, everything I've said about time, it's true for us. In our daily life, it's a good way of thinking about time, but it's not true at all in the universe at large, or if we just make things more precise. So what I'm going to do in these 40 minutes is tell you exactly why it's wrong, what is wrong in this picture of time, what do we know about a better picture of time, and what we don't yet know. And what comes out from this discussion, you will see, is that time is far from being this simple, long line with a past different from the future measured by clock altogether. It's much more complicated than that. And in fact, we understand some part of it, but not all of it. So let me start from, I'll list three completely clearly understood facts that show that this picture is wrong, and then a couple of hours which we are not very sure about, but indicate more problem with this picture. Let me start from the first one. In a sense, that's the easiest one, but it's a more surprising one. Let's take two clocks. And suppose these are very good clocks. These aren't very good clocks. This is my grandfather. But suppose they were very good, okay? Now, they both indicate the same time, okay? The right time. I move one up. Okay? I wait a little bit, 1, 2, 3, 4. I come down. If these were clocks good enough, the one up has stayed up will be ahead of the one down. This is a fact. You cannot check this with these clocks because they're not good enough, but today we have in laboratories very good clocks which are precise in 1 part in 10 to the 15, 1 part in 10 to the 16, fantastically good clock. And this can be measured at the difference of altitude of a few centimeters. So 10, 20 centimeters today, this experience is done in laboratories on Earth to sort of move a clock up, wait a little bit, come it down, and is ahead for the other one. A little bit, of course. That's why we don't see it, right? You go to the mountain, you come back, and your clock is still in time with everybody else. It isn't. It's just that the distinction is so small that our clock misses it. So the amount of time that passes from here to here depends on where you are. If you're in the mountains, then more. If you're the Earth, there's less. What actually causes this is the Earth. The Earth is a big mass, and the big mass literally slows down time, in the sense that clock near it goes slower. Not just a clock, our thinking goes slower, a flower blossom slower, a pendulum has a slower oscillations, and so on and so forth, okay? So time goes at different speed depending on where you are. And if you go near a big mass, like Jupiter, the effect is bigger. If you go near a black hole, which is a very concentrated mass, the effect is even bigger. So if I could go near a black hole, which is just an issue of money, right? So yeah, I mean, I'm a scientist. I don't understand anything about money, but you do deal with money. And the reason we don't go next to black holes, we don't build starships, is not because it's impossible, it's because it's too expensive. Black hole is coming on us. we don't want darkness. We want light if we can. Okay, so if you can keep... No, please. Okay, whatever. So now we're in the black hole. So if I could go near a black hole, okay, and stay there 10 minutes, if I could close enough, then I move away from the black hole, I come back on Earth, and on Earth, a century has passed. So it's easy to go to the future. You just go near something very heavy, wait a little bit, and you go to the future. And you find the children of your children grown up, say, oh, granddad, what are you doing here? Okay? This is not science fiction. It is in some Hollywood movies or something like that, but it's not science fiction. It's reality. We know that the Earth is like that. We know that reality is like that. The first to figure this out is, of course, Albert Einstein a century ago. In fact, this is completely contained in his theory that was written in 1915, so a century and 103 years ago, 4 years ago. But you know, for long it was the strange equation of this strange theory. Nowadays, this is measured clearly and cleanly in the laboratories, which means that these lines, it's much more complicated. In a sense, there is a different amount of time from here to here going up, or from here to here going down. This is already shaky. Point number 2. It's a little bit more clear, but it's a number of facts we know well, which is the following. I said that the past is completely different from the future. There's no doubt about that. We grow old, we don't grow younger. However, it came as a surprise in the history of physics. It started back in the 18th century, in the 17th, 18th century, but it became more and more clear as long as the basic equations of the worlds were worked out, that in the basic equations of physics, there is no distinction between past and future. The grammar of nature doesn't know about the past and future. Now, this surprise. How is it possible that out of fundamental equations which don't distinguish past and future comes out our reality, which seems so different from past and future? Well, good. Thank you. We're out of the black hole. The key is the realization that is old, is a sort of 19th century realization, that every time there's a distinction between past and future, there is heat, something thermal. And one way of thinking about that is that suppose you have Let's see. Suppose you have a pendulum, and you look how it moves, and you take a movie of it. Okay, you have a pendulum. You take a movie of it, and then you project the movie backward. You cannot distinguish the forward and the backward. Okay? However, if you wait enough, after a while, by friction, it slows down and it stops. Now, if you project the movie backward, it doesn't make any sense, because all alone it starts moving, which is absurd. So, friction breaks the difference between the past and the future. But friction is what? Is little heat. The energy of the movement, the mechanical energy, is transformed into heat. That's what friction is. If you throw a ball, it goes forever. If you take a movie and project it backward, it moves forever in the other directions. But in our real world, there is always friction, and the ball slows down. That's, again, presence of heat breaks the difference between past and future. Now, the point is that the difference between past and future exists only when there is heat. In our brain, our thoughts are oriented. In our brain, there is heat production. Plants grow, and there's heat going on. There's heat that makes them grow, and so on. So unless there's heat, there's no difference from past and future. Okay, good. So maybe there is something that breaks the difference between past and future. It's just heat. But what is heat? Heat is just the fast movement of the molecules, of the atoms, which move mechanically. But in mechanics, there's no difference between the past and the future. So where does the difference between the past and the future come from? Well, it comes from the fact that when we think about heat, we are not thinking about the individual movements of the molecules, but we are sort of averaging out, right? The difference between a hot glass of water and a cold glass of water is only that in one case they're moving very fast, the molecules, in the other they are not. And we don't look at the single molecules. We sort of give an approximate, averaged measurement of the movement by saying it's hot. And that's how things feel hot. So the difference between the past and the future comes from the fact that we're not looking at the details, but we're averaging out. And that's quite shocking. I repeat, the difference between the past and the future comes only from the fact that we're not looking at details, but we're averaging out. It is a fact. It was slowly understood by Boltzmann, by people like that in the 19th century. It has become more and more clear because physicists expected, well, maybe we're going to discover something that breaks the difference between the past and the future in the basic equation of physics. There isn't. So it's a statistical thing. It's a perspectival thing. It's because we don't look at the detail that the past is different from the future. But the past is enormously different from the future, right? I mean, we grow old, again. We have pictures of the past, not of the future. Well, because we do an enormous amount of averaging, right? In a single glass of water, there are an Avogadro number of molecules, which is a huge number of molecules, 10 to the 26, whatever molecules, an enormous number of molecules. So it's in this lack of perception of the details that the difference between the past and the future come out. It's not a totally clear story. If you don't find it clearly, it's because the scientists don't have it completely clear. There's a lot of debate about that. But it is a fact that the difference between the past and the future comes only when you zoom out and look at things in sort of a foggy way. It depends on the ignorance that we have of the details. So in a sense, there's an aspect of time which is only due to our ignorance of the details. And that's point 2. The difference between that direction and that direction is only in the perspective we have about things. 3, and that's the third very solid piece of information we have about the world. Something we know for sure, okay? But this third one, in my opinion, is the most shocking discovery of modern physics. It also goes back to Einstein, but it also took a century for the scientists, the community of scientists to digest it. I said that the entire universe is in some point, which now is moved here, and that's the present. and we all have a good idea about the present. We are all in the same present right now, right? Not 10 minutes ago, not 10 minutes in the future, now. Now. And now something is happening on a distant star. Now something is happening on a distant galaxy, on Andromeda or some other galaxy. Now, what do we mean by now? Let's be precise. I see you now, you see me now, right? Do we? No. Why no? Because we know that light takes some time to travel, okay? So the time takes light for going from me to you. It's short, but it's a nanosecond, a few nanoseconds. But it's not zero. So you don't see me now. You see me how I was a few nanoseconds ago, and I don't see you now. I see you how you were 2 nanoseconds ago, and you are far away there. I see how you were several nanoseconds ago, and you see me how I was 7 now. So we don't see each other in the present. We see each other all out of phase, all wrongly, so to say. So what do we mean we are in the same present? Okay? Now, this is irrelevant for us, because a nanosecond is far below what we perceive. Nanosecond is nothing, right? Our brain distinguishes badly a few hundreds of seconds. A good musician can. Nanosecond is nothing for us. So we can say, I see you now, you see me now, we are in the same now. But it's only because of this approximation. If I was in Andromeda, the time lights take to go from Andromeda to here, it's millions of years. So when we look at the stars and when we look at the galaxies, we see them millions of years ago, of course, with time light. So if I have a friend, and if I'm in Andromeda, I call you, hello, okay, a million of years later, sort of you say, hello, and I have to wait 2 millions of years to say, it's a very long conversation. And the notion of now disappears, doesn't make anything. In fact, if you go precisely, I don't want to go into the equations in the detail, if you want to go precisely in the equations that describe this structure, you realize that to define a now, it's impossible. It makes no sense. For what we know about the structure of the geometry of space and time, which we know well, and all the recent discoveries, like the measurement of gravitational waves and so forth, have reinforced our understanding of that. If you go into that, into the mathematics, you see very clearly that there's no sense whatsoever to say what's happening in Andromeda now. Doesn't mean anything. In the history of Andromeda, there is a time which is certainly past us, because we can send a message and whatever happened after is past. There is a time which is before, in the past, which is before the moment in which a message was sent, which I receive it now, here, which is the past. But in between, there is a huge interval of time, which is neither past nor future, which is a sort of super extended present, which in Andromeda lasts millions of years. And between me and you lasts just a few nanoseconds, the travel time of light. Okay? So now is not a good notion in the universe at large. There is no point in which we can say the universe now is something. Now, this is a fact. It's something we have understood very clearly, but this is an astonishing fact, because it means that, how would I put it? What is real? Well, is real what exists today, okay? The Roman Empire is not real, it existed in the past. So it's real what is existing now, but there's no now. So what is real? What does it mean to be real? Well, philosophers are discussing that. Theoretical physicists are discussing that. But this has to do with what we mean by real, what we mean by existing, which becomes more confused. The fact is that the world as a whole is organized in a way such that our clearly intuitive notion of now, it's only a little bubble around us, which depends on how precise we perceive time. If we perceive time up to a nanoseconds, it's just a few meters. If we perceive time like we do down, I don't know, to a millisecond, the entire Earth is in a common now. Okay? But no more, no bigger. Now is a bubble around us. These are the three strongest pieces of evidence very clear, I'm talking about established physics, not about speculations, that indicate that this picture of time is completely wrong. There's more, as I said, because everything I've said so far disregards quantum mechanics. We know that the world is quantum mechanical, and when you fold quantum mechanics in, things become even more confusing, because clocks in quantum mechanics can be in funny states which are sort of quantum superposition of two different states. So even locally, you can say that between this event and this event, the time is not unique. The interval is not unique, but it's a superposition of different intervals. And my job, I mean, what I've done all my life is try to build a quantum theory of gravity, quantum theory of space and time. And if you try to do that, you try to write equations, you have to fold this in, and the usual notion of time disappears altogether. In fact, in the equations that I write, I and my colleagues write, there's no time variable at all. If you want to do quantum gravity, you forget the notion of time. What do? You have variables that describe the world, the position of this, the temperature, the height, the standard variables you describe the world, and you describe how these variables vary with respect to one another, and you forget time. That's how you do quantum gravity. So the notion of time is just thrown away. I hope I've confused you enough. Now let's come back. Okay? We have gone deep into this disappearance of time. Now let me come back from this world without time, at the quantum gravity level, which we don't yet understand well, to our usual notion of time, because after all, like the flat Earth, right, to some approximation, the Earth is flat. So what is approximation where we recover this idea of time here? Well, it's a long story, but to recover our notion of time, we have to take approximation step by step from fundamental physics to our common reality. The first one is forget quantum mechanics. I mean, quantum mechanical phenomena are at small scale. We don't see small scales. Forget the quantum aspect, okay? And if you do that, you go back to Einstein's picture of space-time, which don't have this strange fuzziness, but in which time is not a line. It depends on where you are in some funny way. That's the first approximation. The second approximation is that, all right, time goes at different speed and so on and so forth, but space-time where we are is pretty simple. We are not near a black hole. We are not near a very big mass. So all these phenomena are very small phenomena I'm talking about. So forget about them. Good. So now we have at least common intervals. What about the present? Well, to actually realize that there is not a common present all over the universe, you have to be very far, and you have to consider the fact that things move at one velocity, possibly a high velocity, one with respect to one another. If we are close enough and we're not moving, zipping around too fast, we are sort of all in a common bubble of present. So we have our present. It's a bubble, but it's still our good present. Okay? What about the direction of time? As I said, here things are not completely clear. I mean, philosophers are discussing, physicists are discussing. But if you fold in the fact that we don't see the details, that the world is made by zillions and zillions and zillions of little teeny things, molecules, atoms, quanta of space, photons, all these teeny things, and we don't see the details, from this ignorance come a particular perspective such that the future is different from the past. All right, it's not totally clear, but that's where the origin of the distinction between the past and the present comes from. So we sort of understand, with some holes, how from a fundamentally timeless reality, we get back to this picture of time. But does it really? Because time, it's more than a line. Time passes. What is this flow of time? It cannot be in physics, because physics doesn't have time. The fundamental equation of physics don't have time. Where it comes from? The time of our experience, the exponential time, as the philosophers call it, is not really the time of physics. There's a gap in between. Where does it come from? Well, it comes from our experience. And our experience comes from the way we are done, from the brain we have. we have a complicated brain, and we relate to the rest of the world via the senses and the complicated calculation that happen in our brain. And what does our brain does? Well, it brings in the information, it keeps elaborating it, it keeps predicting the future on the basis of the past, and anticipate what happened. And this is the machine that creates our illusion that is time for us. The amount of study today in neuroscience that try to figure out how our brain works is in large quantity focused on this process of producing the future, computing the future on the basis of memories. If you think for a moment, and this is an old observation, first of all, made by philosophers. Husserl has written pages and pages of that, but in fact it goes back to St. Augustine. It's a remarkable observation. We know that time flows. We know that there is duration. How do we know, given that in any moment we only have experience of the present? How do we know about the past and the future? St. Augustine writes, when you listen to music, suppose you listen to music, you hear the melody. How can you hear the melody, given that in any moment you only see one sound, one note? Well, the answer is clear, because you remember the previous ones. Not only you remember the previous one, but you that's how music works. You can anticipate what comes. Sometimes you're surprised, but sometimes you're not surprised. And memory, music, is the core of time, right? Music is the art is an art that lives only in time. It's made by time. So it could exist only because there's memory and anticipation. And our brain is essentially a memory machine. Memory used to anticipate the future. There is a book by a neuroscientist, an American neuroscientist. The title is Your Brain is a Time Machine. So this means that this image we have of a present, a past, a future, it's not really about how nature is, but it's about how our brain works. We remember something about the past, not much in fact. The past there, who knows what's happened there? Well, we have studied, maybe there are dinosaurs then there's a Big Bang there, who knows what's there, and the future, who knows? Maybe an atomic war, maybe not. So it's our memory as anticipation, what we really mean when we talk about time, which is somehow connected to physical time, but loosely. What we talk when we're talking about time is the product of the activity of our brain made by memory anticipations, which adds to the physical time a lot. Last point. It's still not enough. There's more in time. And I think this is, to me, the most interesting aspect of this story. Why did you come listening a lecture of a physicist on the nature of time? I mean, if it was on the nature of, I don't know, some chemical interacting with you, nobody would come here, right? But time interests us. Time touches us. Time is not neutral for us. In fact, it's dramatically not neutral for us. First of all, because we live in time. We can't even think about ourselves outside time, right? We could think ourselves outside space. Some religions do, right? You die, you're outside space, but you still exist. But could you think yourself outside time? How could you think not in time? So time is structured to the way we are made. We are time things. And time is attached to our sort of deepest emotion, because we lose things because of time passes. In fact, we lose everything because of time passes. In Buddhism, in the pillars of Buddhism, there's the idea that life is sufferance, but life is sufferance because of the impermanence of things, because you're attached to things, and you lose things because time passes. So in a sense, time is the source of all our suffering. Also our joy. Time is what brings us things which give us joy that weren't before. So time is not emotionally neutral for us. It's very talking to our emotions. We know we're going to die. That's the quintessential human emotion with respect to time. Now, philosophers who have discussed time from the most extremely different perspective have both made this observation of how much time is emotionally charged for us. You find this observation in Heidegger, and you find this observation in Reichenbach, which are philosophers of most extreme philosophical position possible. And I think that this is a key observation because this sense of passage of time, which is created by our brain in this game of memory and expectation, is not just a computing machine that does its own. It's something which is has motives and struggle with the loss that comes with time. So I think that the emotional aspect of time is not a sort of fog, like scientists usually think, right? Forget emotions so you understand it better. But if you forget emotions, you don't understand time better. Because this emotional aspect of time is a key aspect of what time is for us in our daily life. For us, time is, yes, the time of Einstein, yes, the time of Newton, yes, the time of thermodynamics, but it's also the time of our brain, and it's also the time of our emotions. So it's these layers, all these layers that makes the complex structure of what we call time. And unless we look at all of them, we just don't understand what we talk about when we talk about time. So time, at the end, I think the emotion of time is not the fog that prevents us to understand what time is. It's actually, to a large extent, what time is for us. Thank you.
Ladies and gentlemen, we have a few nanoseconds for questions. In the front here. We'll bring you a microphone.
Let's stay up so it's longer.
Yeah. Okay. Use mine.
Thank you very much, Professor Rovelli. My question is very simple. You said that as we go up or down, there's a difference in time. So we have spaceships that don't go to black holes, but they do go to Mars. They've gone even to the outer solar system. And there is communication between the Earth and those spaceships. My question is there a difference in time?
Oh yeah, definitely. There's a difference, and it's measured. It's absolutely measured. Yes. Not only that, but you know, the satellites of the GPS, the thing we have in our cars to tell us how to drive the machine. It works with communication with satellites. When the Americans put out the satellite, the first set of satellites, the physicists told engineering that was the Pentagon, it was an army thing, careful, because time up there goes faster. And the system worked with satellites with clocks that sort of broadcast the time. And so the physicists said, careful, because the clocks there are going to faster than what you expect here on Earth. And the engineering said, of course, we're going to keep this in account. But since it was an army project, the generals of the army, the American army, when they saw the report, said, come on, time passes. I don't believe that. So the first system was built, this is the 80s, was built without keeping this difference of passage of time, and it didn't work. So the GPS of your car works by taking account the fact that time passes faster there than here.
Thank you very much.
Two questions, two very quick ones. The first one is time travel possible? If so, how to achieve that? And the second one, in the geometry of the universe, is there some sort of superposition where I, as a human, could see past, present, and future at the same now? If that makes sense. Star Trek inspired, of course.
The first question is time travel possible? Well, I mean, a cheap answer is our life is a traveling time, isn't it? I think what you want to know is, can we travel faster, or we come back to the future? Now, to time travel to the future is certainly possible. As I said, it's just an issue of money. It's your business, not my business. I mean, the equations are clear. You want to go to the future, build a starship fast enough, make a long run, come back, you'll be in the future. Coming to the past is much harder. It's not impossible, but it's extremely harder, precisely because of this thermodynamics, you have to fight against probability, in a sense, against thermodynamical probability, and that's make it very harder. So at present, if you ask me, are we going to be able to travel to the past, I would say probably not. Not because it's intrinsically possible, but because we have to work against the number of molecules, which are too many. The second question was much more vague. We are studying quantum gravity, so yes, in principle, there might be quantum superposition of different timings. What this produces in our experience, it's not much, I think, because in our experience, quantum phenomena are rapidly washed out because in the macroscopic things wash up quantum phenomena. That's why we don't see quantum phenomena in our macroscopic life. So I think there are going to be effects that you can only pick up with very precise measurements and not with big sort of macroscopic experiential facts.
We'll take the gentleman in the front row and then the gentleman 3 seats to your right, please.
Yes, Professor. In quantum physics, we go for the very large to the very, very small. So, and there is this phenomenon about entanglement, where two particles or two something communicate. Do they communicate at the speed of light? Do they communicate in now? Are they in the same moment of time, those two entangled particles?
There is a lot of confusion about the actual sense in which two entangled particles communicate. They don't communicate. They definitely don't communicate. It's a theorem in quantum theory. You cannot use one of the two to send a signal to the other. It's a called no signaling theorem in quantum mechanics. They communicate in the sense if you measure something here, measure something here, there are some correlations, but the only way to check these correlations is to look at both of them. So you have to wait for information to come back together. So there's no direct communication between the two. So the answer is no. I mean, the entanglement does not break in any sense the idea that communication cannot go faster than light. In fact, a lot of current research came out from the effort. When the entanglement was figured out first, the scientists said, oh, great, let's use it to make faster than light communication. There were projects to the Pentagon. And then it became clear that this is impossible. It's very subtle, the sense in which entanglement, it's an entanglement between two different systems. It's not just that they are connected.
I had a statement and then a question. The statement was right here in the front.
Okay, sorry.
The statement was, I found it ironic as you were saying that there's really no such thing as time, that you kept looking at your watch. But the question is, can you think of a practical application where the dissociation between our physiological perception of time and the reality of time, is there a way of harnessing that into the real world?
It's a very good question. Let me first comment on your observation. That's up, okay, and that's down. And it's very convenient to talk about up and down. We know that in the universe at large, there's no up and down. Okay? We understand perfectly well what's happening. We sit on a rock, there is gravity, so up and down are just here, relative. This does not mean talking about up and down wrong. It just warns us that talking about up and down, it's good here and not all over. The same with time. Now, your question is very good. In fact, with a group of medicine psychologists, philosophers, physicists, we put out a big request of money to the European Union, to a big grant to study exactly this question. And we did not get the grant. There was a lot of very good people in the request, but I think the referee had a point, namely, yeah, great idea, but you have anything concrete in mind? And we didn't. There are vague ideas, but too vague.
We'll take the gentleman at the back there.
Does this work? Oh yeah, it does. Look at that. Well, I've never taken physics. I skipped it, and I'm not an astrophysicist, but you talked about emotional time. Time may not exist. And I'm just wondering how perception fits into that, because when you're in certain places, if it's a theoretical, then sometimes you're in one place and time goes by really, really quick, and another time, oh my gosh, you're in science class, and it goes on forever. But the question is, where does that fit into the world? Because if time is all a theory in your mind, then in reality, is time actually moving quick when you're really interested in something, or is it just, how does perception fit into that? And I don't even know if that's a physicist term or not. I'm not sure.
Yes, look, in a strange, funny way, right? Because in a sense, we all know that time goes at different speed. That you just gave examples of. Sometimes 1 hour is fast, sometimes 1 hour sometimes hour feels short, sometimes it feels long. Now, however, somehow we went to school and we were taught, all right, this is part of your psychology, but behind that, there is a clear physical structure of time which is measured by clock and is the same for everybody. So, in a sense, what I'm telling you is that, yeah, that's right, but only partially right. That clear common structure of time itself is far from uniquely defined, is much more rich and full of variety. So in a sense, the psychological perspective of the time flow, it's more close to the nature of time than the simple measurement of a clock. When we talk about time, it's not just a single position of the hand of a clock, and therefore those that seemed funny phenomena to be discarded are more relevant to understanding the nature of time than what seemed 50 years ago, 100 years ago.
Thank you. Quick couple of questions. One is, does physics explain how you're able to sort of look in your past? There are people who can do that, and people who have sort of foresight of what's coming up and can tell pretty exactly what's going to happen. And then secondly, I understand that going back in time may not be physically possible because of chemical reactions and everything else, but what about if you could just go back a day and you could sort of correct a mistake that you have made, and not
you would like that,
5 days back, right?
We all would like that so much.
Yes.
I'm not sure which exactly phenomena you're referring to, but I think a lot of phenomena like predictions about the future have been shown totally convincing, in my opinion, or very largely convincing, that they're illusions, they're not true. You can predict the future, of course. Theoretical physics is about predicting the future, right? I can predict the position of Venus tomorrow in the sky with very, very large, in an extremely reliable way, but that's not what you're talking about. So I think no. I mean, the strange phenomena that we didn't understand have nothing to do with this flexibility of time that physics is making emerge.
We have one final question over there, the gentleman.
So my question might be related to the concept of flow, which the gentleman back there talked about. Time tends to move differently based on the activity that you're in, but it has to do with personality types and how we experience loss of time in terms of longing for time, and whether that relates to sort of the impatient personality. Does that make sense?
Well, I'm not a psychologist at all, so but definitely there are individual differences in perception of time. I cannot say more than that. There is an interesting amount of research on the perception of time in different animals, right? So an animal that has a much faster perception of facts than us, it can process things much faster than us, like a bat that flies or a fly, or an animal or a plant I'm assuming that the plant has a perception. I don't know. Maybe they don't. But imagine an animal that receives information about the world once every second instead of one every hundreds of seconds, as we do. Would have a completely different sense of the flow of time, right? If you think, we have a very clear idea of how fast time goes, right? But it doesn't make any sense how fast time goes. How fast with respect to what? So what we're talking about, when we're talking about the speed of the flow of time, is our own, is the rapidity at which our brain works, and the amount of memory that our brain can hold and process. So yes, it depends on the brain, it depends on the species, and presumably depend on the different experiences, the different personal psychology.
Carlo, we're over here on the right. We have one final question request from Carlos.
Yes, as a scientist, are you an optimist about humanity or not much so?
I wish I was an optimist, but I'm not. I think that humanity is making big mistakes right now because it's increasingly aggressive toward itself. It's destroying the planet for real. I think the destruction of the planet is more real than what we're told. There's a destruction of species, there's global warming, of course, and there is belligerence between nations, and it seems to me that instead of collaborating, we are working against one another, and that's unfortunately the direction in which our species is going. We are too many. I am pessimist, and I very much hope to be wrong.